Today we're going to talk about factoring polynomials completely. This is kind of the last section of this chapter of factoring, and it's kind of tying a lot of the stuff together. We're first going to talk about when we start seeing polynomials with 4 terms, not just the 3 terms that we've seen or the 2 terms, where we're going to be trying to get together the terms into pairs, and we're going to factor with the GCF, which goes back to the beginning of this chapter, and then look for that common binomial factor, which we just did in the last section when we were kind of splitting the middle. So this is called factor by grouping, and it's very similar to what we just did in the last section with trinomials. This one is now going to incorporate the 4th terms, and we just have to talk about how to deal with that. Then we'll talk about what does factoring completely mean to finish off this note sheet. So for number 1, we have x to the 3rd, which is a little bit different than what we've seen, plus 3x squared plus 2x plus 6. Obviously, there's nothing that can be added any further. Those terms are already broken up as unlike terms. So what we're going to do first is we're going to take and group the first 2 together and the last 2 together. Okay, so we're just going to think of them as 2 separate parts. And what we're going to do is look for the greatest common factor of each of the pairs. So looking at the first one, so just focusing right now on this, what is the GCF of x cubed and 3x squared? Well, the GCF is going to be take out x squared. If I remove x squared, then the inside would be then x plus 3. So that's just removing the greatest common factor from the first 2 pairs of terms. So then I would look at the second one and I would say, okay, now I want to look at this one. What is the greatest common factor of this pair? Well, between the 2x and the 6, I can remove 2. So if I divide out a 2, I would get the x plus 3 on the inside. So that's just finding the greatest common factor of those 2. And again, we have to notice a couple of things for this to work. This x plus 3 binomial has to be there for both. It has to be a common x plus 3 binomial. But once I have that, and I do have that there, we can then do what we did in the last section and say we now have x squared plus 2 times x plus 3. And again, we want to continue by looking at that first binomial and say, is there anything else that I can do to simplify that? Well, there's nothing in common between x squareds and 2's that I could remove. I can't use this. This is not a perfect square binomial. This is not also the dots or difference of 2 squares binomial. So there's nothing I can do with either of those. So this would be what we would call factored. Again, you can always do a check using FOIL. X squared times x, there's your x cubed. X squared times 3 is 3x squared. 2 times x is 2x. Now notice those 2 can't be added together because this has the 2 and this one doesn't. And then the 3 times the 2 is the 6. So it does give me back to my original question, which means that would be the factored of each of that polynomial. All right, on the second one. So this one, again, can't combine any more of those terms. So what I'm going to do is look at the first 2 as a pair and the last 2 as a pair. So looking at x squared plus x. Well, there is an x that is the greatest common factor of those 2 terms. And if I was to remove those, the x would leave x plus 1 on the inside. For the second binomial, if I look at that, I have a y in both terms. So the y can come out. If the y comes out, y divided by y is 1. xy divided by y is x. Now obviously, an initial looking at this, I don't see the exact same binomials, but the second one over here really is the same thing as x plus 1. We can use the commutative property just to kind of rewrite it so we do see that common binomial there. And then once we have the common binomial, I can put those first 2 together as one binomial, and then that common binomial becomes the second pair that goes together. And there is your factored set. Next, we want to talk about that factoring completely. We always want to make sure we go as far as we possibly can with those. On that first example we saw, we had a binomial of x squared plus 1, but we said we couldn't go any further with that. But on this one, for example, right off the top, you see x squared minus 1. This is a situation that if I was to see this as one of my binomials, that's my dots, which I could go a little bit further. And we always want to make sure we go as far as we can if we are saying it is completely factored. So notice the x squared plus 1 can't be written as the product of polynomials with integer coefficients. This is what we call unfactorable. It's not that we can't solve it, and we'll show that coming up in a later lesson, but we can still solve it, just not with factoring. So a factorable polynomial is factored completely when it is written as the product of unfactorable polynomials with integer coefficients. Once you get to the point where each of the different polynomials in your factor are not factorable any further, then you know you've gone far enough. So here are some guidelines. I'll just kind of talk through a few of these. So to factor something completely, think about all these steps. And you just kind of run through them real quickly as you go. Factor out the greatest common monomial factor. So this would not be factored completely because we can see that there is a 3x in each of those terms. Once you take the 3x out, you do get the 3x times x plus 2. Neither of these could go any further, so then you know you're done. Here you always want to look for those difference of two squares or the perfect square trinomial. Right here you see a perfect square trinomial, right? We would see that the x squared is a perfect square, the 4 is a perfect square, and we would get the x plus 2 squared. Remember on the dots, you could see something similar to this. If it was x squared minus 4, that would be looking at a dots pattern where you would say it's x plus 2 times x minus 2. Again, those two binomials can't go any further. That would be where the dots would come in. Then third, you would factor the trinomial in the form of ax squared plus bx plus c. And again, you want to do your product of ACs that add up to the b value. We get our two binomials. And we always look at this and we say, could I go any further? Which in this case, I can't. On the last one, with the 4 terms, you're using that grouping method we just talked about, where you put together the first two and you kind of pull out the greatest common factor. You put together the second two, pull out the greatest common factor. You get that common binomial, which in this case probably would have been the x minus 4. And you always would look at this to see, could I go further? If this was x squared minus 1, you would go another step further because it would be a dots. This is not factorable, so I would be factored completely. So let's go through a couple of these factored to see how far we can get. So looking at this first one, I want to first say GCF. Always look for your GCF first. Right away, I can see that there are 3's in each of those terms, and I can also see x's. Now the highest of my x's is just plain old x. I can't take out x squareds because the last term only has 1x, and I certainly can't take out x cubed. So taking out the greatest common factor first, I can pull out x squared. I'm sorry, 3x. When 3x comes out, that would leave me x squared for the first term, plus 2x for the second term, and minus 6 for the third term. Then I want to look at that one right there and say, is x squared plus 2x minus 6 factored completely? Again, we want to look at, this would be back to the lesson where we had the coefficient of our x squared as a 1, or the a as a 1. So I'm looking for factor pairs of a negative 6 that would add up to a 2. So if I look at those numbers, how do I create 6's? Well, I can create it with a 1 and a negative 6, a negative 1 and a 6, a 3 and a negative 2, and a negative 3 and a positive 2. That's the only way I can create negative 6's. Now in this case, there's nothing that will go together there to create the sum of a 2. So as much as you feel like this should go further, this would be considered factored completely. On the next one, again, my very first thing should be look for the GCF. Well, in this case, I see the GCS as 7. There's definitely 7 goes into 7 and 28. And x squared would be the highest of the powers that are in both. Once those come out, I would get x squared, and I would get minus 4. Now here's a situation where sometimes people will leave at this point and say, that's done, I'm finished, I have the binomial. But again, this second one, the x squared minus 4, this is the dots pattern. There is something else that I can do here, so I need to go one more step to say x squared, x plus 2, and x minus 2. Now you can say that this is factored completely. And again, you can always check all of these by multiplying all of your answers back to make sure that it ends up where you started. Next, we want to look at an example where we're solving an example to finding the solution, not just factoring. So we still have to think about, how do we solve an equation? Well, again, when we did our equations, we had to get that 0 on one of our sides. So for this example, the very first thing I need to do is I need to get that negative 10x brought over to the left side. I would get 2x cubed plus 8x squared minus 10x equals 0. Now I can focus on the factoring part since I have that 0 on one side. So looking at that trinomial, I can see that there's a common 2x in all three terms. When I take out 2x from the first term, I have x squared remaining. When I take 2x out of 8x squared, I have 4x. And when I take 2x out of negative 10x, I get minus 5 equals 0. So again, to factor completely, I want to look at this trinomial again to say, is x squared plus 4x minus 5 completely factored? So again, I'm looking for factor pairs of the negative 5 that would add up to a 4. And if I can kind of use my common sense here, I want to use the negative 1 and the 5, which would multiply together to get the negative 5, and they would also get the sum of the 4x. So just to bring that over here now, I can turn now this x minus 1, x plus 5 equals 0. So remember, our zero product rule says that if any of these are going to give me the answer of a 0, then I know that those are solutions. So this is where I would make each of those set to 0. And now I just solve. So for the first one, x equals 0. For the second one, I would add 1 to both sides, so x equals 1. And the third one, I would subtract 5 from both sides to get x equals, that looks like an 8, but it's a negative 5. So my solutions, or my roots, remember we're calling these solutions roots, our x's are 0, 1, or negative 5. So for our last example, we have a terrarium in the shape of a rectangular prism. They give us the dimensions as w plus 4, w, and 36 minus w. We are told that the volume of the terrarium is 4,608 cubic inches. They talk about the length is more than 10 inches, so we want to keep that in mind when we get down to our final answer. And then we want to figure out what is the length, width, and height of the actual terrarium. So we know that volume of a rectangular prism, we know that volume is length times width times height. So in this case, we have 4,608 is the volume. We have 36 minus w times w plus 4. So one of the things that we're going to have to do is we're going to have to get that 4,608 brought over to the right-hand side. So unfortunately, what we first have to do is kind of build up that right-hand side and multiply all that stuff together. So if I just focus on these first two, 36w minus w squared and w plus 4, 4,608, 36w squared, when I do my FOIL, plus, what is that going to give me, 144w minus w cubed minus 4w squared. So that's just putting all that stuff together. So I probably want to rewrite this a little bit into standard form. So I'm going to subtract the w to the third. I do have some w squares to put together, so I now, after I subtract 36w squared and 4w squared, get 32w squared. I have the 144w, and we have this 4,608 on the other side. So now what I need to do is get that 0. So I'm going to subtract 4,608 to both sides. And now we have 0, negative w cubed, plus 32w squared, plus 144w minus 4,608. So now I need to start looking at factoring this whole thing to see what we can come up with. So I'm going to put this first two together as the pair and this second two together as a pair. So the first two, what I see in common is I see that w squared in both. I'm going to pull out negative w squared because we ideally would like to see a positive w on the inside of our binomial. So if I take the negative w squared out of the positive 32w squared, I'm going to get negative 32. So that's the first one, just pulling out the GCF. On the second one, the numbers are a little bit harder to kind of figure out, but basically what happens is you have 144 goes into 4,608, and if I take out the 144 from 144w, I get w on the inside, and it actually goes in 32 times, which is, works out perfectly in this case, because now I have that common binomial of w minus 32 and w minus 32. That then means I can finish off my grouping by saying I have negative w squared plus 144, and then over here we're multiplying it by w minus 32. Now, this doesn't really look like anything at first, but if you look at this one here in the first binomial, if I was to rewrite this one and flip it around just a little bit, hopefully we can all see that is the same thing. That is our perfect dots pattern. Perfect square in the front, perfect square in the second term, and we have a subtraction. So because of that, that tells me that I'm not factored completely yet. I can go a little bit further here to figure out that we can break this down a little bit more to 12 plus w, 12 minus w. And then obviously we still had that other w minus 32 from the other binomial. So that would be as if we were just factoring it completely. Completely meaning all the way down so that those polynomials can't break down any further. So now we have to look at what does this tell us for our problem. So basically for the problem, we're looking at, with our zero product rule, we're looking at 12 plus w equaling 0, 12 minus w equaling 0, and w minus 32 equaling 0. So for the first one, w equals negative 12. For the second one, w equals 12, and w equals 32. So unlike a regular generic trinomial or polynomial, we have a context, and we got to figure out, do these numbers make sense? So going back up to our problem here, what we need to know is that the length is more than 10 inches. So we want to find the length, the width, and the height of the terrarium, remembering what our initial binomials monomials start out as. So if I look at my terrarium, first thing I think we need to ask ourselves is, can we have a width, or the W, as a negative number? Remember, the W would be this side dimension right here. That was the W that we looked at. So obviously the answer is no. We're going to throw that one right out right away. Can't have it as a negative. So then I would look at the second one. So the second one, if I was to say that 12 is my W, that would mean that the height would be 12 plus 4, which is 16, because they told us that it was W plus 4. And then it would also tell me that the length at the bottom would be 36 minus 12, which is 24. Now, looking at the second 32, let me just see if we can kind of make sense out of this one. If the W is 32 right there, then 32 plus 4 is now 36. And 36 minus 32 would make my length 4. Now remember, up above, it was very clear that it said that the length right here is more than 10 inches. So with that in mind, I now have another number that we are not going to include. This number right here can't be my answer for the simple fact that the length does not equal 10 or more. So the answer to this is, this first piece right here means that the length, the width, and the height, so the L would be 24 inches, the width we had found was 12 inches, and the height would be 16 inches. So hopefully that made some sense. It kind of ties together this entire chapter. If you have any kind of questions, feel free to let me know, and we will certainly be able to talk about it when we see each other next.